Hello, I'm Shuichi Ihara, DataDirect Networks. Today I talk about the raster, the metadata fundamental, the benchmark result under analysis. So the slide title are a little bit changed, but most of the content is the same. So first of all, the raster metadata, this is one of the critical performance metrics for many raster users. Several years ago, the raster only focusing on the throughput, but now the raster deployed not only large HPC site, but also the small and the even the other not HPC site. Fortunately, there are a couple of the very important feature is landed in the raster mainstream, from the raster 2.3 and 2.4. The SMP, the scaling the patch, this is one of the important patch to improve the single metadata server, the performance improvement. Then we also now have the multiple, the MDS option using the DNE. The people also are interested in the small file, the performance on the raster file system, but the metadata performance is really related to the small file, the performance on the raster file system. So also the people doing a lot of the metadata benchmarking and collecting the metadata statics information. However, so the metadata the benchmarking are still a little bit difficult and still a little bit the mysterious. So because the metadata benchmarking is not simple. So there are several the metadata access pattern or metadata type. So that we have to then make sure the differentiation of each of the metadata type. Then also the people imagine the metadata server, the server resource, the impact of the metadata performance, but there is not much the guideline. So what's the hardware resources impact to the metadata performance? So this presentation, basically, so we're using the standard metadata benchmarking tool. Then collecting the fundamental, the baseline, the number, then analysis the metadata performance on raster file system. So raster metadata benchmarking tool. So there's two measure benchmarking. It's wrong. There's something wrong. So first of all, the MDS survey. So this is a long, it changed the word, but there are two measure the benchmark tool. So one is the MDS survey, another one is the MD test. So the MDS survey is basically the part of the raster code line. Then it's similar idea, the OBD filter survey, so we can run the benchmarking for the OST side. So MDS survey, so we can generate the metadata load on the MDS side without a client. Then we can simulate the metadata performance. So MD test, so this is a measure of the benchmarking tool for metadata, not only the raster, but also the general the file system, the metadata performance. So it supports the MPI, so we can run the MD test on the raster client, then it's scaling well. It also supports the several metadata operation, then access pattern. So we use the MD test for this testing. So before that, I talk about the raster metadata, the scalability. So I have to mention about today's the single client metadata performance limitation raster file system. So you can take a look at this graph. So this is a simple the single client metadata performance. Just the MD test on the single client, then we can measure the file creation, the start and removal. Start operation, that red bar is scaling well. However, even the number of the threads increased. The file creation, the file removal on the single client is not scaling. Because this is today's raster design limitation. So even the client can send the MDS metadata request to MDS simultaneously. However, so MDS need to store the last transaction ID of per client into the MDT. So the limitation is there. So only there is the slot per client to store the last transaction ID per client. So it's serialized. So even the client can send the many requests, but finally it's serialized in the MDT. So there is a very interesting, the ticket is opened to support the multiple slot per client to keep the last transaction ID in parallel. This is still under development by Intel and the Blue. Hopefully we can see the much better the single client metadata performance after the patch is landed. So we have to take care about the single client metadata performance. So meantime, so we use the MD test. However, so we changed the MD test benchmarking to a little bit. So because as I mentioned, the single client performance is limited. Single client metadata performance is limited. So we mount it. So we use the multiple mount point on the single client. Then the MD test to recognize the multiple mount point. Then sending the MDS request through the multiple mount point on the single client. So this is helpful if we don't have enough number of clients. So if we have so many thousand clients, so we don't need this change. But so normally number of the client is for testing is limited. So we use this modification. So this is helpful. So we can generate the heavy metadata the operation from the single client. So this is a background. So the patch is developed by the Liang Chen. So the SMP scaling work. Then we rebase the patch against the latest MD test. Then clear up the code. Then add the additional enhancement. So this tool are helpful not only benchmarking, but also the stress testing and the regression testing and the MDS server sizing, as well as the performance optimization. So this is a quick example when we use the modified MD test. So left side, so this is the standard one single mount point on the Lustre client. So as I said, only start operation is scaling when number of the threads is increased. But if we have the multiple mount point on the single Lustre single client to the file system, so a new syntax of the MD test is supported. So we can point it the mount point at the one command line on the MD test. So once we can use the command line interface, the command line. So you can see the right side. So when number of the thread is increased, so the file creation, the file removal operation is the scaling as well as the start operation. So we can use the multiple. So this is only for test use. So, but this is very helpful. So we can generate the metadata requests from the single client. So this is the benchmark configuration. So, we had the 4 OSS, then connected to a DDN, the SFA 12K40. Then we have the 400 nearline SAS drives for OST. Then we also set up the 2 MDS, then connected to the SFA 12K40. We also populate 8 SSD for MDT. Then total we have the 32 clients over the InfiniBand. They're connected to the server over the InfiniBand. We install the Lustre 2.5 for the old server. However, we set up the Lustre master branch for the client. And also we also set up the 1.8 client just for comparing. So this is a configuration overall. The metadata benchmarking method. So So there is the three operation to directory and file operation. So directory file creation, the start and removal. Then also we have the couple of the access pattern. So one is a unique directory and a shared directory. So unique directory means, so each of the process, creating the own directory, then creating under the own directory for own directory. The shared directory access pattern. So there is only one single shared file, a single shared directory. Then all of the process, creating the file under the shared directory and the start and the removal. So there is only one single shared directory. That is a shared directory access pattern. Then finally, we also run the benchmarking with the stored access pattern. So the stored means each of the metadata operation that's sliding with the CPU. So for example, when the CPU 0 creating the file to the specific directory, then the next time the process 1 or the process 0, the process 1 is calling the next call, the start, to the process 0 created the file. And then finally, the process 2 calls the unlink operation to process 0 is created, the file. So each of the operation is sliding to each of the process. So let me introduce the benchmark result from here. So first of all, the metadata benchmarking, so how much the hardware resource, the metadata server, the hardware resource impact to the Lustre metadata. So we used the 32 client, then each of the client has a 32 mount point, then total the 128 mount point, then we can simulate the 124 the Lustre client. Then we create the 128 million file for total. Then the tested server, the 16 the CPU core, but we changed the CPU speed from 2.1 gigahertz up to the 3.6 gigahertz. Then make sure so what's the metadata performance impact by CPU speed. So left side, the directory operation, the right side, the file operation. This is a unique directory access pattern. So all of the result, so how much the performance improved compared to the baseline number, which is 2.1 gigahertz, the CPU speed. The file operation, the significant performance improved by CPU speed. Then file removal, the directory removal, also improved up to the 38%. However, the directory, the creation is not much improved, only 20%. Even the CPU speed, the CPU speed increased more than 70% from the 2.1 gigahertz. So this is the same testing, but except the shared directory access pattern, the same number of the client, the same number of the mount point. Then we also use the same CPU speed for the testing. So the file creation also, even the shared directory access, the significant performance improved. Then directory file removal also improved 30%. However, in the past, we didn't see the directory removal operation much, but in the shared directory, we saw the significant performance improved more than 50% by CPU speed increased. Even in this case, the directory creation was still much improved, even the CPU speed improved. So this is another benchmarking, still the CPU impact, but in the past, only the CPU speed, we just make sure the CPU speed impact. In here, So number of the CPU core impact. So we keep the CPU speed 3.3 gigahertz. However, we're changing the CPU number of the CPU core from the 8 core up to the 16 core using without a logical processor. This is a very interesting result. So we see the significant scaling with the performance, the scalability on the start operation, on the directory operation. However, the directory creation, the directory removal not much improved. Even the 100% of the number of the CPU core increased. However, the file operation it's scaling linearly, the number of the CPU core. So we see more than 80 or 120% is performance improved when number of the CPU core from 8 to up to the 16 core. So file creation is much impacted by number of the CPU core. This is the same benchmarking, but except to the shared directory access. So directory operation, so there's no much the performance improvement except the file directory removal. So directory removal, so we saw the only 40% improved, but the start and directory creation is not much improved. Nothing much improved. So file creation, it's the scaling well, but we hit the performance limit on the 12 CPU core. So we didn't much see the performance improvement from the 12 CPU core to the 16 CPU core. Then also the other thing, the start operation for the both type, the directory operation and the file operation, so we didn't see much the performance improvement by number of the CPU core. So this is the CPU impact to the shared directory access. The next benchmark result. So this is the scalability testing from the 16 CPU, 16 the number of the thread up to the 24 the number of the thread. Overall, all the operation the scaling well. Then once we achieve the maximum the metadata operation, then we can keep it can keep then the metadata the performance as sustained. And also we set up the DNA option on the different MDS server. Then we also run benchmarking using the DNA. Then the DNA helped a lot. Then we saw the double performance of the single metadata performance. So it's linearly scaling the number of the MDS server and the MDT. So one of the exceptions, the directory creation is not much scaling. So even the number of the threads is increased. So this is the one of the limitation. So this is also the scalability testing to the shared directory. Overall, it's well. It's not much higher than the unique directory. However, so most of the metadata operation is achieving the 80% of the unique directory access pattern, which is good. But also, we still see the directory creation is lower than file creation. It's not much scaling. So we more investigated why the directory creation is not scaling well on the raster file system. So we assumed the problem in the ext4 level. So we ran some of the benchmarking with the ext4 without a raster. Then we confirmed the same behavior, same benchmark result on the ext4 level. So directory creation is always slower than file creation. So when we take a look at the ext4, the code line, there is a couple of the functionality, the function, taking a lot of the cost. So which is the get block and the map blocks. So the directory creation is different the operation from the file creation. So one of the exception is when directory is created, so directory creation need to allocate the block, extra block for the dot file. This is a special block. So these costs are low. Then we profiling the data. Then these two functionalities are a lot of the cost. So in order to avoiding this feature, this limitation, so there is the functionality in the ext4 in the new kernel, which is inline data. So inline data, the idea is the small file stored into the inode itself instead of the extra block allocation. So once we run the benchmarking and the analysis with inline data and without the inline data, once we enable the inline data, so significant the cost is reduction. So not much the get block and the map block the cost there. Then finally, we also run the MD test benchmarking with inline data and without the inline data. Then significant performance improved. Then the directory creation with the inline data, there is no much the performance difference with the file creation. So this is really the significant performance improved. So we try to this feature in the raster file system. However, so inline data is not available in the LDISC-FS because the LDISC-FS level, there's another feature, the DIR data. So DIR data and the inline data is incompatible today. So we didn't test it. We couldn't test the inline data with raster file system yet. So in order to improve the directory creation, so we might have the similar idea in LDISC-FS, or we might need to support the inline data feature in LDISC-FS. So we just opened the ticket to investigate. So this is another benchmarking. So normally, when people doing the MD test benchmarking, in order to make sure the metadata performance, only metadata performance, so the people using 0-byte file, so there's no amount of the file size when file is created using the MD test. However, so this is useful for the only benchmarking, but so in the realistic production system, so basically the file has the amount of the file size. So on this benchmarking, so how much the metadata performance impact by the file size? So we run the MD test using the amount of the file size from the 4K byte to up to the 128K byte. However, we didn't much see the performance that drops by number of the file size. So we see the same performance, even the 0-byte file and 128K byte. So it's not much the performance drops, so which is good. So raster, the small files is still good, as well as the 0-byte file. However, so you can see, so we didn't get more better performance because the small file performance is bound on the metadata performance. So we cannot get better small file performance more than metadata performance. This is the final benchmark result. So this is a storage option. So MD test supports the storage option, so which can help avoiding the local locks in the cache for the start and the unlink operation after the file creation. So normally, without the storage option, so all of the the process, so all the same process is creating the file on the start, then finally removal. So everything is the same file associated with the same process. But once stride option is enabled, so each of the operation is sliding to another process. So this is much the cost expensive the operation for the Lustre file system, which is fine. But we saw that some the performance degradation the Lustre 2.6 client. So once we confirm to make sure, so in order to make sure, so this performance degradation, I just run the same benchmarking with the Lustre 1.8 client. So Lustre 1.8 client is significant. The performance is better than 2.6 client for the stride option. So we just opened the ticket for this regression in the 2.6 client. Then now working on the investigation. This is a quick summary. So as I showed some of the benchmark result, the hardware impact. Regarding the hardware impact for the metadata performance. So the MDS server, the resource, the significantly affect the Lustre metadata performance. Then also, so not always the number of the CPU core and the CPU speed to the unique directory is really helpful. However, the CPU cores or number of the CPU core is not much help to the shared directory access pattern. So we only tested the 16 CPU core. So now the more number of the CPU core server is available. So it's worth to try more number of the CPU core for test. Then also, as I showed some of the benchmark result, so metadata performance, they're highly dependent on the metadata access pattern. For example, the directory creation, the file creation is so different. And also the unique directory access pattern and the shared directory access pattern is also different. The stride option, so it makes the production use, the metadata use case. So we can avoiding the local lock in the cache, the client. Then also, we didn't match the file size impact on the metadata performance. However, so we only tested the 14 only 14 the OST. So we really need to do more testing the large number of the OST. So more future work. So we reported the number of the known issue, the optimization. So we have to investigate more these of the ticket. Also, we really very interesting in the single client metadata performance improvement. So we wanted to take a look at that ticket as well. Then the future investigation. So right now we just collecting the fundamental, the baseline number using the MD test. However, so the real world the metadata use case scenario is different. So we really need to make sure, so what's the metadata access pattern on the real world. On the small file access pattern as well. Then at this moment, we didn't much see the OST data structure, the performance impact. However, so number of the OST is maybe the impacted. So we need more we need to test more large system. So as far as we tested the DNA, the scalability testing, even the number only 2 MDS server, but we see the linearly the scaling using the DNA. However, we also need to test the more number of the MDS and the MDT, and as well as the OSS and OST. That is my presentation. Thank you.
I have two questions. Number one, do you see the impact of MDS cache size on the MDS performance? Because you haven't talked about that. So that is number one.
Okay. So on this benchmarking, so I only see the CPU impact, but we also tested the 128 gigabyte memory and the 506 gigabyte memory. So we only test the 1 million file. So in that case, it's not much impacted. Okay. So we need more testing, so more number of the file, but maybe they impacted, but we don't know yet.
Okay. And the second question is, you have shown that with the increase in the file size, that MDS performance was constant. But will it change if we have more number of read-write operation being done on the client side? You know, you may have many LSEECs and some read and write operations. So as the number of file size increases, maybe more read-write may get generated. So that may impact the MDS performance. Is it correct or wrong? I don't know. I'm just thinking aloud with you.
Yeah, so that is, so we more investigate the more realistic metadata operation. But so you mentioned the read-write is a more OST side, right? So it's not much impacted, but when we create the file, of course the OST and the OSS is the CPU workload. So maybe they impacted. So we really need to the more mixed workload, not only just the MD test.
Okay, thank you.
Did you have some testing with hot cache on MDT, like previously start large number of files and run start again to see an impact of Lustre memory allocation and flushing ext for caches? So for OST we have some problem. Read-only cache is flushed at ext for internal data, and for each write, ext4 need to re-read this data. But how it is affected for MDT?
On the MDT?
Yes. So we may have a situation when a new operation on MDT allocate in memory and flush some ext4 caches. And
right.
ext4 need to re-read and bitmaps or other in memory. So
yes.
it will. How did you test this?
Right. So this testing basically just a sequential the testing, the creation, the start and the removal, at the same one job. So that is as you mentioned, that is also the more realistic the benchmark, realistic production the metadata operation. So for example, the file is created the one month ago, the store into the ext4. There's no cache on the MDS. So but we have to start on that file. So what is the impact? So I think that we have to run the similar benchmarking, but at this moment only just baseline number, collecting the baseline number. Then after that, so we more investigate the more realistic metadata workload.
My question more about, did the system release system caches first, or it is release Lustre caches first? If it is release a file system cache first, we will be second read from disk. But if we release a Lustre data first, we will be recreate this, and this less cost of operation.
Well, we can run we can make a similar workload. So once you mount the MDT,
run second state test. First start test will be create a hot cache on MDT. Second start cache will be see how it will be changed. If we will be too much disk reads from MDT disk, we will have less performance. But if MDT will be good cache use, we will be some start improvements.
Yes.
So it is what this question.
So this is only, you know, as I say again, so this is the single job, right? So not much aware of the cache, but so your said is correct. So we have to do more the metadata access pattern for the test.
Are you planning to do some of the tests with ZFS to see if it can improve the overall performances of the cluster?
Sorry?
ZFS. Are you planning to test ZFS instead of Extend 4?
I would like to test, but at this moment, not much. But so this is a good. I think that this is a good start. So we're collecting the baseline number with the ext4, the LDSCFS. Then after that, we can run the same benchmarking with the GFS as well. It's a future plan.
Actually, so Gabriel's presentation will talk about ZFS metadata performance later. The other question I had, you talked about testing with more OSTs, the metadata performance. Actually, I'd be more interested in testing with fewer OSTs, because I think that the object creation rate of the OSTs with a fewer number will actually limit the metadata performance and scalability. So that might, I think it would be more interesting to go that way.
Yeah, I agree. Yeah, so right now only that's true. So we also tested the less number of the OST as well as the more OST. Yeah. So at this moment, not much tested yet, but yeah, we have to test.
The last question.
What was the RAID configuration you were using on your SSD devices? Have you tried different RAID configurations and even different kind of storage devices, such as SAS devices?
So this is only the RAID 1 configuration. So for MDT, because you know this is SSD, so not much seek time, right? So in the past, so when we use the drives, so the RAID 1 is more less the seek time, reduce the more seek time, but the SSD, so this is not the part of this benchmarking, but we are doing the fundamental benchmarking for the RAID volume with RAID 6 or RAID 1 or RAID 5 on the SSD. However, so that we didn't match the performance differentiation on the SSD because of no much seek impact.
And did you ever try it with SAS devices?
Sorry?
Did you ever try with SAS devices? With SAS devices?
Yes. Sorry?
With SAS devices?
No, this is SSD.
But did you ever try with the influence?
Not the same the environment yet. But yeah, we can. So this is a additional plan. So to compare to any. So in this presentation we only focusing the CPU, the impact for MDS. So the next plan, so we also there are a lot of the stuff. So a lot of the combination. So the next plan we have to run the disk side impact.